purpose of this video is to help you learn how to use the Jet 10 aircraft design and analysis software by demonstrating how to use the software to optimize an aircraft for a particular design mission. The aircraft we'll be optimizing is the YF-22. You can see the geometry of the YF-22 represented over here on the left side of the graphical user interface. The parameters that describe the aircraft are shown here, and in particular describe the fuselage down here. And the aircraft described by those parameters is drawn in 3 views up in the upper left-hand corner of the spreadsheet. Then in the middle of the spreadsheet at the top we have aerodynamic analysis. Then just left of center is a thrust and drag curve for whatever altitude we specify here in the box. And to the right is weight and sizing analysis results, and down in the bottom is the mission analysis. This is the design mission for the YF-22, and if you watch the other video you know that this is these are the design performance requirements that the Air Force finally settled on after asking for much more stringent requirements and learning from constraint analysis that those weren't feasible. The constraint diagram is drawn here, and the whole package lets you optimize the design for any particular set of requirements. In this case we have the YF-22 design mission and constraints, and we're going to optimize the aircraft for those requirements. Now the F-22 is not optimized strictly for the requirements that are shown here because some effort was made to make it extremely maneuverable and able to do post-stall maneuvering with vectored thrust and large pitch control surfaces. And that costs something. And we're going to, in this exercise, determine a little bit what it costs to have that great maneuvering capability. We saw before in the other video that the requirement to have high sustained G's was completely unaffordable. Well, let's see how much it costs to be able to do that post-stall maneuvering. So we'll start by eliminating that giant pitch control surface that allows the F-22 to be so maneuverable. We will not type a 0 in the area. We never do that in jet. It messes up some of the ways some of the coefficients are normalized if you set a surface area to 0. So instead we just make it very small. So the first benefit we expect, of course, is that less wetted area will result in less drag and less fuel burn. And also, if we look on the weight tab, we notice that the pitch control surface weighs 1,000 pounds. So the combination of less weight and less drag should allow us to reduce the aircraft's takeoff gross weight. Partly because the aircraft will burn less gas. On the other hand, we might be worried that removing that pitch control surface will make the aircraft very unstable. Right now, Jet shows estimates that the aircraft static margin is minus 3.7%, and that's probably a pretty good estimate for the actual aircraft. So if we remove that pitch control surface, what's going to happen? Well, let's watch. Let's watch this cell M10, and while we set the pitch control surface area to 0.001. Alright, here we go. Well, isn't that interesting? The aircraft got more stable. Now, it probably got more stable because the CG moved forward. We removed 1,000, 1,100 pounds, something like that, very far back on the aircraft. And so the CG moved forward, and so the static margin increased. But why didn't removing all that surface area back there make the aircraft very unstable? The answer is here in the Aero tab. If we look down here at the calculation for d epsilon d alpha in cell A40, we see that it's nearly 1. That means that that pitch control surface can't contribute to the aircraft's stability, because every time the aircraft's angle of attack changes by 1 degree, the downwash also changes by almost 1 degree, so that the angle of attack of the surface itself doesn't change. And so the surface doesn't contribute to the stability of the aircraft. And we know from talking with folks who participated in designing the YF-22, that was the case for the actual aircraft. So our spreadsheet and our aerodynamic and stability analysis is giving us a correct prediction of what actually really happened on the real YF-22. Alright, so pitch control surface is gone, good riddance. What else can we do to optimize this airplane? Well, first off, now we have a lot of extra gas. We got rid of 1,100 pounds and we got rid of some drag, so the amount of fuel we have increased and the amount of fuel we need decreased. And the way the fuel increased is we specified an aircraft max takeoff gross weight. We only type numbers in the white boxes. The blue box is where we calculate how much fuel we carry. And the way we do that is we take our input aircraft takeoff gross weight, subtract the weight of the landing gear, the airframe, the engines, and the expendable and permanent payload. And whatever's left must be fuel. And as long as there's room to fit the fuel in, and there's 41 cubic feet of volume remaining according to our estimates. So, what do we do with all that extra fuel? Get rid of it. So let's go to 62.5 on the takeoff gross weight. And now we have, well, we still have 400 pounds. Let's go to 62.1. And we can probably go to 62,000. When you reduce the aircraft's weight, you also reduce the fuel burn. There we go. That's pretty good. Alright, so we have saved a couple $1 million per airplane. I didn't highlight it, but when we started this out, the estimate for the aircraft cost was about $100 million a piece. And now that estimate is $98 million a piece. So we've saved $2 million by reducing the weight of the airplane, which allows us to reduce the materials that go into it, the labor that goes into it, etc. Well, what else can we do? One of the things we notice is that this wing has a fairly high taper ratio. Now, if the wing sweep was less than 45 degrees, we would have a rule that says the taper ratio can't be below 0.23. And that's because when you have less than 45 degrees of sweep, you really don't get leading edge vortices, and so you'll experience tip stall. The tips will be very highly loaded. But when you have more than 45 degrees of sweep, typically the separation on the wing rolls up into a leading edge vortex, and that thing is more resistant to tip stall. So we could go to a lower taper ratio at this point. And let's see what good that would do for us. Let's reduce it to 0.1. Okay. And yeah, saved a couple hundred pounds. Let's try 0.05. Alright, let's save some more. And we can go ahead and reduce to like 61.6. And that was just a little too low. But let's Let's go 61,637. There we go. Alright, now something funny happened here on the wing. The ailerons are kind of hanging off now. And I need to do something with those ailerons anyhow, because you notice the aileron column is labeled ailerons/elevons. And we want to turn those things into elevons since we no longer have a pitch control surface. So the way we do that is we just put the ailerons right on top of the flaps. And we do that just by referencing the cells. Now we don't copy down this reference because the formats are not the same in every cell. And if we copied down the reference, then we would mess up the formatting. You can see here we have feet in the format, and this one is degrees, and so we wouldn't want feet in there. This one format for the airfoil section, actually we can't reference that cell. It's a special format, so we just leave it. It's fine the way it is. Alright, so we've got elevons now, and we'll make those things bigger, say 70, and we'll increase the aspect ratio to maybe 8 so that we have nice elevons along the trailing edge of the wing. And let's see where we're at. We've saved more than $2 million, $2.25 million, something like that. And there's more work to do. Notice here on the constraint diagram that the plus, which is our actual design point, is located to the left of the 0, which is the desired or optimum design point. That means our wing's too big. So let's see what happens if we make the wing smaller. Let's try 800. Okay, now our wing is exactly the right size in terms of wing loading for the optimum wing loading. We have a pretty good airplane now, and oh, by the way, we save some more weight. A smaller wing weighs less, so I can reduce this to maybe 61.4. And when I do that, let's try 61.3. When I do that, I can probably move the plus sign over to the right even further. Now, one thing that's limiting me right now is the landing distance. But remember in the other video we said that actually we would be willing to just have the sum of the takeoff and landing distance be 8,000 feet, the length of the runway. That allows us to accelerate for takeoff, reach takeoff speed, and then abort on the remaining runway. Right now our takeoff distance is like 1,700 feet, and it only takes 3,600 feet to stop. So if we lowered the takeoff distance to say 3,000, and the calculation in cell X13 subtracts whatever takeoff distance we have from 8,000 and allows the remaining distance to be our landing distance. That moves the landing constraint over to the right where it's really not an issue, and it allows the optimum point to move over to the right as well. So once again our wing is too big. So moving in a optimizing direction, let's try 750 for our wing area. Okay, and we can drop down to say 6,100 now, and let's try 60,800. Yeah, that other was 61,000. And let's try, we're a little short on gas, but let's just try to keep moving in the smaller wing direction. We got our gas back. We can go 60,600. Alright. And maybe 60,500. Okay, now there's some other places we can save on weight, make this airplane smaller. The vertical tails are now too big. We have a CN beta of 0.0028, and we really only need 0.002. So let's reduce the size of the vertical tails to say 160, 140. Okay, but the tails aren't really coming to the end of the airplane, so let's put them back a little ways. Now they're hanging just a little bit off, but I can reduce a little bit more, so let's say 130. And there we go. The tails fit on the airplane. CN beta's good. We saved another 700 pounds. So 59.8. Oops, too many zeros. 59.6. Alright. So, at this point, we have our plus sign in the middle of our circle. We have a size takeoff weight that's very close to our actual takeoff weight, and a sized wing area that's very close to our actual wing area. So we can use sizing and optimization to try to find a more optimum wing. Let's look over here. We were at 2.23 for aspect ratio. Let's see what higher aspect ratios might do for us. And we were at 48 degrees of sweep, so let's see if less sweep might help us out. We could try other ranges, but let's try this one and see what we can learn. So here we go. We're watching. Oh, there's some really big solutions here showing up. Definitely we don't want the combination of aspect ratio 2.2 and sweep of 50. So let's see if we want 2.2 at all. No, definitely if we go to higher aspect ratios, we don't need that 2.2. So let's change this to 2.4 and do it again. And notice that we have 3.2 showing up twice because the old calculation wasn't erased here. But we can fix that. Just click on here and change the area that's being plotted. So now we're just plotting this much area. The other extraneous 3.2 went away. And we have a pretty good indication that aspect ratio 3 and a sweep angle of 44, let's see here, sweep angle of 46 is optimum. Well, 46 is okay because as long as we're over 45 degrees, we can have that lower taper ratio that we specified. If the answer had been 44, we would have had to do some iterations on that because now we can't use that low taper ratio. It'd probably actually be okay at 44, but we just don't want to crowd too close to aerodynamic problems. So it says 46 would be a better sweep angle, so let's try that first. Well, it burned more gas, but it also saved more gas. So I can go to 59.5 now. Okay. And it also said that higher aspect ratios would be better. It said 3. The 3 makes the wing really heavy, so I'm not sure I want to try to do that. Let's try 2.4 and see if that is a better situation for us. 2.4 isn't really that good either. How about 2.3? Getting closer, but 2.2 is better than 2.23 where we were. Let's try 2.1. Well, there we go. So perhaps the automated optimization helped us a little bit move in the right direction, but our manual optimization says it's worth it to go down even lower. So 59.1. Okay. And the only issue with these low aspect ratios is our sustained turn. We're starting to bump up against the limits on sustained turn. One of the things we might have been able to do if we'd have gone with the recommended aspect ratio is we might have been able to make the wing smaller and move even further down. But this isn't bad. If we look at our price per airplane, we've saved over $5 million per airplane, and that's not trivial at all. If we build 200 airplanes, we save $1 billion on purchasing them. And there's a commensurate savings in NRE as well. There's one last thing we should check before we declare victory. We check the landing gear. Okay, landing gear takeoff rotation is a little bit problematic. We're right on the limits there. But because we moved the CG back, let's look at the CG for a second. Our static margin's -10. We probably should move the wings back to fix that a little bit. Let's try that. Let's move our wing back to say 23. Fix the static margin. It helped things a little bit in some places. And we'll move the strakes back the same amount. What did we go? 3 or 4 feet. Let's go 1.9. No, 1.8. We must have gone 2 feet. Okay, yeah, that looks good. And we can move the inlets back a foot or so that they're inside of the... Of course, we don't want to move the engines. The engines were just fine, so we'll go back and fix that. So this is pretty impressive. We have optimized our airplane even better than it was. We've saved $5.5 million really dollars per airplane. And if we check the gear now, because we moved the wing back, which moved our pitch control surface, which was attached to the wing trailing edge back, we're in good shape in that regard. We can help this a little bit more by moving the main gear forward. Notice that the angle from above the main gear forward to the CG is 23 degrees, and we don't need it to be that high. Let's go to 37.7. We could go 37 point maybe 37.5. Yeah, 17 degrees. Now it's 17 degrees from straight up above the gear to forward to the CG. And we hit the tail at 16 degrees. And so there's no way our airplane will be a tail sitter. This change in the gear also helped us because even with the most forward CG, we can rotate it at 166 knots. So the airplane's quite workable, and we saved $5.5 million per airplane by optimizing, and we preserved the low observability aspects of the aircraft, and in a way, because we made the airplane smaller, we must have also reduced its radar signature. So that's what optimization can do for you.